Hey folks, how we doing? Recording some lectures here for our week 10 content. So this is going to be a pretty short and sweet week for we're going to be mostly talking about activity and equilibrium. And in a previous semester we would have spent a lot more time with this, but because we're a little bit behind, I'm just going to kind of only go through what's important. So here I've got the learning goals. So in this first video, I'm just going to talk about solvent activity. So this first one, be familiar with solvent activity, solute activity, ionic activity, and be able to do calculations involving ionic activity. So I'm going to do an example of that. And that's really the only thing I'm going to do in this first video. In the next video, it's going to be all about equilibrium. Okay? So let's do it. The first type of activity I'm going to talk about is solvent activity. And this is for highly non-ideal solutions. So I gave you that example in the previous lecture of my own thesis work, like a concentrated sodium chloride solution would be highly non-ideal. And so what that means is you don't have a predictive way of calculating its properties, such as vapor pressure. So now this is specific for solvent activity. So I'll write lowercase a for activity, and I'm going to just put of species A, so that could be water or ethanol or whatever our solvent is. So I'll say solvent is indicated by this letter right there, whatever the solvent is. And lowercase a for activity. Okay, activity. All right, so for solvent activity, that equals the observed vapor pressure of species A divided by the pure solvent vapor pressure. So this is for, a solution. So really we're kind of saying this is solvent activity, but we recognize that this is the solvent activity of A in a solution. Okay? So this would be the pure vapor pressure of the solvent. And then now this is the measured vapor pressure of the solution. Okay, and so I showed you that example again with the water and the salt. So we know that when you have a solution of sodium chloride compared to that of pure water, so if I write H2O here, but then now I've got a solution that's salty water, so I'll just say NaCl aqueous. Okay, there's vapor pressure here, and there's vapor pressure here. So we'll say this is the pure vapor pressure, right? And so we know that the pure vapor pressure of the water is going to be greater than the vapor pressure when we add solutes. So this is one of our colligative properties. And in fact, I'll make this, I'll change this to observed to be consistent with our activity. So whatever we measure the vapor pressure of this solution to be, we could calculate the activity of that by ratioing it to the vapor pressure of the solvent. And what would be useful in this kind of exercise would be to look at activity versus like perhaps mole fraction. So as we add more solutes, we see, and actually I should write it as, I could write it in terms of activity of the solvent, but I'll write it in terms of the mole fraction of the solute, right? And we know as we add more sodium chloride, the vapor pressure decreases, so we'd see something like that, okay? So generally activity doesn't have to be for vapor pressure. So it's a general measurement. And so let me draw a line here. And so we'll say in general terms, Okay? Activity is defined as the following. It's the limit of the activity divided by gamma, here, which I'll talk about in a minute. And all of that just equals the mole fraction as this gamma coefficient approaches 1. Okay? So effectively what you're seeing here on this graph, that's kind of what this is showing, right? So on this graph where chi NaCl is 0, and chi NaCl is never going to approach 1. We're never going to have just like pure sodium chloride. We're only going to get to where it's saturated. So, maybe I'll say chi NaCl 0.1. But we know on the top of this graph, if I made this chi H2O, where chi NaCl is 0, chi H2O is 1, right? And so what this thing is kind of saying, this limit is, as you get to a more and more dilute solution, your activity approaches 1, so it approaches the pure case, okay? Hopefully that makes sense. So that all equals 1 as you approach that limit, all right? And so now what that means is, generally, activity is the following. The actual activity, so the activity that you would measure, equals the activity coefficient which sometimes that's referred to as fugacity in the case of ideal gases. But I'm not going to spend a lot of time talking about fugacity. If we had more time, I'd spend more time with it. But it's kind of one of these more obscure ideas, okay? So let's see here. And so, of course, we know as the activity coefficient approaches 1, then the mole fraction will approach 1. So as our activity coefficient tends to the non-ideal value, which is 1, our mole fraction tends to the non-ideal value of 1. Okay? And so we could write this in terms of the chemical potentials. So I could say the chemical potential of the solution equals the chemical potential of the pure liquid plus RT times the natural log of A. Okay, the natural log of the activity. And I'm just going to do some quick algebra here. What we could also do, and this is getting into the statistical mechanics of activity, right? So if I rearrange this equation, so if I subtract these two, so I subtract that to the other side, so I'll say mu A solution minus mu A star. I'm running out of room here, okay? And I'm going to divide by RT. Oh my God, this is terrible. Divide by RT. And now if I take E of both sides, right, then I can see that this is related to that kind of Boltzmann-like formula, right? That the activity is E raised to the difference of the chemical potentials divided by RT, okay? So sorry that that's kind of sloppy there. Okay, so moving along. So we could also come up with a solute activity. And what's important to note, that the activity always equals 1 for a pure, solid, or liquid. This is going to come up when we get into equilibrium, and it's part of the reason why we don't include pure solids or liquids in equilibrium expressions, because their activity equals 1. That's kind of what we were talking about here. As our solution becomes more and more dilute to the point where it's now no longer a solution, but it's just a pure liquid, the activity will be 1. Well, the same is true for a pure solid as well. Okay, the activity is always 1. All right. But if we have now in a solution, okay, and this is the case of an ideal solution, the solute will follow Henry's law, like what we talked about before. So now I'm going to say AB, where now B is my solute. And that's going to be the observed pressure of that solution divided by the Henry's law constant. Okay. And that's dependent on which solvent you are in. Okay. And our limits for the solute go as the following. So AB will approach 1 as gamma B approaches 1. So that's just basically saying as the solution becomes more and more dilute, or as you approach that of a pure material, the activity will become 1. But this is different from the solvent case. The mole fraction here now approaches 0. So in the solvent, the mole fraction was approaching 1. However, in this case, the mole fraction of the solute is approaching 0. So it's more or less saying the same thing that we said before. And so now we can come up with activities in terms of all kinds of different concentrations. So again, this is just vapor pressure. But what about other activities? So we can come up with activities in terms of molalities. I always have to say this out. Molalities. Okay. And so I'll use a J to indicate chemical species J. And so that's going to be, I'll use a B for molality. That'll be the molality of species J divided by standard molality, okay? Where standard molality is exactly 1 mole per kilogram. Of course, we could do this for molarities. And in terms of molarities, this would be then, you know, the molarity of species J divided by standard molarity, where standard molarity is, of course, 1 mole per liter. And then in terms of partial pressures, it's the same as this. So partial pressures, then the activity is, it's just exactly like what we kind of described before, except for in terms of standard notation, it's the partial pressure of species J divided by standard pressure, where standard pressure is typically 1 bar. Now, the reason why we have all of these is because, as we will see, this is going to become the basis for equilibrium. So when we talk about equilibrium, you've been used to seeing it in terms of partial pressures or molarities, but technically equilibrium is in terms of activity, as we shall see. So this is creating the basis of how we can use activity for equilibrium in various concentration or pressure units. So in terms of partial pressures, in terms of molarities, or in terms of molalities. So basically these activities, in this case now, are becoming a dimensionless quantity, right? We're ratioing it to whatever standard base unit, okay? And the last form of activity I'll talk about in this very brief flash lecture is ionic activity. And ionic activity is, again, related specifically to non-ideal solutions, okay, where we have no way of making a predictive basis. And of course, these are going to be for ionic solutions. Sorry, I'm real sloppy in my writing today. So for non-ideal ionic solutions, okay? So I'm just going to present to you the Debye-Huckel equation. So this is called the Debye-Huckel limiting law. Okay? And what this does is calculates the ionic strength. And ionic strength can be, in some ways, a metric for activity for specifically ionic solutions. Okay? And so what really the, ionic strength. And what the ionic strength gives us is really a measure of not only how many ions are in solution, so the higher the ionic strength, the more ions are in solution, but that's also going to create the basis that's going to allow us to calculate the ionic activity. So this equation goes as the following: 1/2 times the sum, and lowercase I is denoting of all species in the solution, Z, this is the charge of the ion in question. So that can be for cations or anions, and that's why it's being squared, so that we don't have to worry about the positive or negative sign. And technically, this is in terms of molalities. So we notice that this is the molality activity. And in the case of aqueous solutions, okay, so what I'll say here, for aqueous solutions, we could make this 1/2 I Zi squared, and we could do this in terms of the molarity. And let's see, for standard aqueous solutions, at 298 K. And the reason for that is because, so we remember that standard molality equals 1 mole per kilogram. Well, this is damn close to 1 mole per liter for water, right? 1 kilogram of water is basically 1 liter of water. It's technically like, 1 liter of water is like 0.9998 kilograms, something like that, right? But reasonably, for these calculations, you can do it in terms of the molarity activity as opposed to the molality activity, okay? So, but now, we still have to be able to calculate the activity coefficient, because I'll remind you that the activity in terms of a solution is equal to this coefficient times mole fraction, or similarly, we could say activity is equal to this gamma times the molarity, okay? And so now from here, there's another equation that becomes part of the Debye-Huckel limiting law, and that says the log of gamma of this activity coefficient equals, and now this is a crazy equation, which it's empirical, so it's based off of data fitting, okay? And so that's negative 0.509 times the absolute value of Z plus times Z minus, so the charge of the cation times the charge of the anion, absolute value, times the square root of the ionic strength divided by 1 plus the square root of the ionic strength, okay? And then so finally, for example, if let's suppose we wanted to be able to calculate some solution property, like perhaps the pH, okay? So up to now, you know that pH is the negative log of the H plus concentration. That's only approximate. You've been lied to. Are you surprised? No, because chemistry is the science of exceptions. Technically, the more correct way to calculate pH is the negative log of the H plus activity. So pH, because it's a solution property, and typically it's a solution property of non-ideal solutions, technically pH is the negative log of activity of the H plus ion. And as we'll see, so this limit is best, so these two equations, best for roughly 0.1 molar and less. So when you have solutions that are 0.1 molar and greater, there's some adjustments that are done to these equations, and we're not going to worry about that, okay, in this class. All right. So let's do some sample calculations to show you where all this comes from. Okay. So here's a couple problems. I'm only going to calculate a few parts of this. So calculate the pH of a 0.1, 0.01, and 0.001 molar solution using H+. Okay, great. Well, hopefully this is a nice stroll down memory lane. pH is the negative log of, I'll just do the 0.1 example, and I don't even need to throw that on my calculator. I know that's going to be 1.00, okay? So now, what if we do it in terms of, oh, and excuse me, because, this is log sig fig rules. Because I have 3 decimals in my log, Is that how that works? Yes, I get three. I have three significant figures in my log, 1, 2, 3. So I get three decimal places, 1.000. Okay. So I'm just going to do that same one using the activity calculation. Okay. And so first I have to calculate the ionic strength. Okay. And so this is using H+. So we'll assume that this was from HCl just to make life easier. So we have H+ and Cl-. An interesting case would arise if we did this with sulfuric acid, if we had the -2, the divalent sulfate ion. And I'll show you that in a moment. Okay. So this is going to be ionic strength equals 1/2. And now I have to sum up all of the charges. So that's going to be 1/2 times Z times the ratio of molalities. I'm going to use the ratio of molarities, but it's going to be a very similar calculation. So that's going to be +1 squared times 0.100 divided by 1 plus -1 squared times 0.100 divided by 1. And when I sum all this up, hopefully you can see what the number is going to be, but I'll do it just for consistency. So +1 squared is 1 times 0.1 divided by 1 is 0.1. So let's just write that out. 1/2 times 0.100. Okay, and then -1 squared gives me +1 times 0.1 divided by 1 is 0.100. And 0.1 plus 0.1 times 1/2 is 0.100. Okay, so why did we even have to do that calculation? Because if we had a divalent ion, it would change the result, right? If we had something that was -2, or if we had something that was +2 or even +3 or +4, it would really change this ionic strength. So therein lies one of the big rubs in ionic strength is as you have, in excess of monovalent cations or anions, ionic strength really changes significantly. Okay. So now what we have to do is calculate the actual activity coefficient. Okay, so that goes as the following. Log of gamma equals -0.509. And of course, this is now the absolute value of 0.1, the absolute value of +1 times -1, which once again, you can see that that's not going to change this result. But if it were a divalent cation, it would be a significant difference. And now that's times the square root of 0.100, okay? And this is now all divided by 1 plus the square root of 0.100, okay? And so let's do that. So that's going to be, so 0.1 square root times 0.509 negative, okay? And so I'm just going to collect this up so I get it all right. So the top half I get to be negative 0. Let's say 161 with the 3 sig figs there in the decimal. Okay, divided by 1 plus the square root of 0.100. Okay. So let's see, 0.1 square root plus 1. Okay, and so now I need to divide that. Okay, great. And so I get that the, I'll write that over here. I get that the log of gamma equals -0.122, okay? So gamma equals 10 raised to the -1.22. So we can see that's going to be less than 1, which it should be, all right? And so let's do that. So I get this now to be 0.755. Okay, so if gamma for H plus equals 0.755, how do we calculate the pH of that now? Well, let's go back. We remind ourselves that the activity is gamma times the concentration, and then the pH will be the negative log of the activity. Okay, so now I can say the activity of H plus is going to be 0.55 times the 0.100 mole per liter. Okay. And so technically we drop out the units because really this is, it's divided by standard activity. So we don't worry about units and activity. We drop the units. Okay. So that's 0.0755. And now if I do pH as the negative log of the activity, you can see this is going to be different than my 1.000, right? Okay, so let's take the log of that. So I get this to be, let's see here, 1.122. So that's significantly different than had we used concentration. I would definitely say that's significantly different because remember, this is a pH measurement. It's a log-based measurement, right? So if you're off by 0.1 in the pH, that's fairly significant. So now I didn't do this for the 0.01 and the 0.001, but what ends up happening, because these are more dilute, the calculation of pH for activity versus concentration for those more dilute examples gets better. Okay, so that's why I chose to only do this 1.0 example, because that has the biggest difference. All right. However, as you approach, like, so we know this is, a pH of 1, and this is a pH of 2, and this is a pH of 3. So as you get to those pHs, you see less and less differences, so less error if you use concentration-based pH versus activity-based pH. But what's important to note, and I'm not going to go into this again for the limit of time, but I know that your analytical chemistry professors are excellent when it comes to teaching you about probes. So as it turns out, what a pH probe is actually measuring is this. This is what actually gets measured. It measures the ionic activity. So it's basically measuring some ratio. It's measuring the activity of H plus ions to some reference point, which is why you calibrate that pH meter. Okay. And also, right, I just did this for monovalent cations, like I mentioned. Had we done this for divalent cations, there's a real significant difference. I didn't put a figure in here, but there's a figure in Atkins that shows you really well how, if you start comparing like sodium chloride to magnesium chloride to magnesium sulfate, you get really significant differences, right? Okay, folks, so I think that's a pretty good amount of lecturing on activity. I'll do one more lecture on equilibrium after this, which will be more or less a review. I might have to do 2 videos for equilibrium, but we shall see. Okay, I'll see you in the next one.